Welcome to Math Science History. Today, we are going to look at how Mayan math was practically used, from the stars to the markets. And we'll walk through the story of how the Dresden Codex was found, preserved, and decoded. I'm your host, Gabrielle Birkjak. I have a background in math, science, and journalism. And by the time you're done listening to today's podcast, you're going to know a great deal more about the amazing and advanced mathematics of the Mayan culture. In the year 415, the infamous philosopher and mathematician Hypatia of Alexandria, Egypt, was savagely murdered by church monks. This murder shocked the Roman community and its government leaders. Hypatia was known far and wide as a respected philosopher, mathematician, government advisor, and a professor. Hypatia, The Sum of Her Life, is a book that I wrote that looks not just at the circumstances surrounding her death, but also at the sum of her entire life. I weave in the details of her education, disciples, Neoplatonic philosophies, female contemporaries, and the many mathematics that she wrote and taught about. There is truly more to Hypatia's life than her death. Hypatia, The Sum of Her Life, written by me, Gabrielle Birkjak, is now on sale on Amazon. Buy your copy today. Today, we're traveling back more than 1,000 years to explore a remarkable mathematical system developed deep in the jungles of Mesoamerica. Before calculus, before Newton, before Europe fully embraced the idea of zero, there was the Maya. Their number system, calendar, and understanding of zero rivaled and, in some ways, exceeded their contemporaries around the world. We're talking about Mayan mathematics. We're going to explore how their base 20 system worked, how zero was conceptualized centuries before it became mainstream, and how modern scholars like Ernst Förstemann helped us rediscover this knowledge. We are going to decode the brilliance of the Maya, one dot, one bar, and one shell at a time. The Maya civilization thrived in what is now southeastern Mexico, all of Guatemala and Belize, and parts of Honduras and El Salvador. At its peak, from roughly 250 to 900 CE, known as the Classic Period, the Maya developed intricate city-states like Tikal, Palenque, Copan, and Chichen Itza. These were not only political and economic centers, but also cultural and scientific hubs, brimming with artisans, priests, architects, and astronomers. From these jungle metropolises, the Maya observed the skies with astonishing dedication. They tracked solar cycles, lunar eclipses, and the movements of Venus and Mars. Time wasn't just measured, it was revered. Every ritual, harvest, and political event was synced with the cosmos. Their concept of time was cyclical, not linear, and that cyclical rhythm formed the very backbone of their culture. The past, the present, and the future all echoed one another through calendar cycles. To make sense of these vast cycles, some lasting thousands of years, the Maya needed mathematics. Not just tally marks or trade-based counting. They needed a system that could measure not only the number of cacao beans in a bag, but the number of days since the creation of the world. So they built calendars that could do both. Their temples and pyramids weren't just religious structures, they were astronomical instruments. At Chichen Itza, the famous pyramid of El Castillo casts a serpent-like shadow during the equinoxes. At Uxmal, the buildings are oriented with the rising and setting of Venus, which was central to both warfare and prophecy. These alignments weren't accidental. They were deliberate, math-driven expressions of cosmology in stone. But to accomplish this, the Maya needed a number system that could handle immense time spans and cyclical logic. They needed more than counting. They needed structure, scale, and zero. Unlike our base 10 decimal system, which likely stems from counting on 10 fingers, the Maya used a base 20 or a vigesimal system. So why base 20? Well, one theory suggests they counted on both fingers and toes. Another theory suggests that the base 20 system could more easily accommodate complex calendar math. In the Mayan system, the numbers 0 through 19 are the building blocks. The number 20 is like our 10. It starts a new positional level. 400 is 20 times 20, 8,000 is 20 times 20 times 20, and so on. So that number 20 starts at the basic positional level, kind of like where we put our tens. Each position increases by the power of 20, except in the calendar system, which I'll go into later. The genius of the system is its positional structure. Like in our own decimal system, where the digit 3 means something different in 30 versus 300. The position of symbols in the Mayan system changes their value. The Maya managed large-scale calculations with extraordinary economy of space. For example, a large number like 2,482 in Mayan numerals would be represented with just a few glyphs across 3 levels. So, the Maya had a really beautiful, simple way of representing the numbers. The number 1 was represented by a dot. The number 5 was represented by a bar or like a hyphen. And then the number 0 was represented by a shell. Basically, it was an ellipse that they would put a design within, so it looked like a shell. So number 1 would be a dot, 5 would be a bar or a hyphen, 6 would be a bar and a dot, because that's 5 and 6. 10 would be 2 bars next to each other. 13 would be a bar with 3 dots. And then the number 20 would be a new place value, being the second level up. So for example, in the second level, number 20 would be represented by a dot, because 1 times 20 is 20. The Mayan number system was vertical in structure, which was a striking contrast to the horizontal layout we are used to in modern numbers. So think of it as a layered stack, where each level holds a specific value based on the powers of 20. At the bottom level is the units place, representing the ones. The next level up is the 20s place, and then that's 20 times the value below. And above that is the 400s place, because 20 times 20 is 400. And then the 8,000s place, which is 20 times 20 times 20, would be the level above that. So I'm going to provide an example on my website at mathsciencehistory.com. And as a side note, while you're there, please click on that coffee button. Because when you donate a cup of coffee or 2 or 3 or 4 to mathsciencehistory.com, you help to support this podcast, which is a free educational platform for everybody, including college students that I'm seeing are listening to this in droves now, which is very exciting. Thank you so much. And thank you to all of you who have donated to the podcast. Your support means the world to me. Anyhow, back to the Mayan number system. So imagine a vertical stack with 2 dots at the third level, 1 dot at the second level, and 3 dots at the bottom. So the 2 dots at the top level, the third level, that would be 2 times 400, which is 800. In the second level, that's 1 dot. That would be 1 times 20. Then at the very bottom, we have 3 dots. 3 times 1 is 3. So the number equals 823. That's it. It's that simple. Just 3 glyphs neatly stacked. No separate symbols for hundreds or thousands, just dots, bars, and shells arranged in vertical layers. What makes this system so elegant is that it's positional and exponential, like our own base 10 system. A dot in one level doesn't carry the same value as a dot in another. This allowed the Maya to write large, complex numbers efficiently and compactly, a necessity when they were carving in stone or painting on delicate codex pages. But this wasn't just about mathematics, it was about meaning. Mayan numbers weren't hidden in ledgers or buried in calculations. They were proudly and artistically displayed on temple steps, stelae, ceramic vessels, and city walls. On public monuments, large dates from the long count calendar were recorded in these vertical stacks of glyphs, often surrounded by images of kings, gods, or cosmic symbols. They gave weight to political power and religious legitimacy by anchoring a ruler's deeds within the context of time and celestial order.
We'll be right back after a quick word from my advertisers.
Even within sacred texts, like the Dresden Codex, the numerical stacks served not just to track astronomical events, but to guide rituals, forecast eclipses, and calculate offerings. The glyphs were rendered with such care that numbers themselves became aesthetic and spiritual elements. The vertical format wasn't just a style, it reflected the Mayan worldview, where time, space, and hierarchy were experienced in layers. Just as their pyramids rose in stacked platforms toward the sky, so too did their numbers build meaning upward. Math wasn't only functional, it was visual, ritualistic, and cosmic. One of the Maya's most extraordinary contributions to the world of math is their early use of zero. Zero was not merely a placeholder in Mayan math, it was treated as a full digit. They represented it with a shell-like glyph. This allowed them to express quantities with place values clearly, such as 20, 1 in the second level or 0 in the base, or 400, 1 in the third level or 0 in the second, 0 in the base. While zero was also independently developed in ancient India, the Maya were one of the earliest civilizations to use zero in a positional system, dating at least to the 4th century CE. This gave them a functional edge over many ancient cultures that lacked such a concept. Historian Georges Ifrah calls the Mayan use of zero, quote, one of the most striking inventions ever to emerge in a mathematical culture from the old world. The Maya developed multiple calendars. They were basically timekeepers of the universe. They developed a 260-day ritual calendar called the Tzolk'in. They developed a 365-day solar calendar called the Hab, and they used another calendar called Long Count, which was used to track vast historical and mythological spans of time. The Long Count is especially interesting from a mathematical perspective. It used a modified vigesimal system. For example, 1 kin equaled 1 day, 1 wino equaled 20 days, 1 tun equaled 18 winals, which was 360 days, 1 katun equaled 20 tuns, which was 720 days, and then 1 buktun equaled 20 katuns, which was 144,000 days. What's interesting for the tun, which was 18 winals or 360 days, they used 18 instead of 20 because it was likely to approximate the solar year, which was 360 plus 5 extra days. This calendar allowed them to date events thousands of years in the past and in the future. The famous 13.0.0.0.0 long count date corresponds to December 21st, 2012, which is not the end of the world, just the end of a great cycle. It marked the completion of 5,125 years since their mythological creation date of 3,114 BCE. Their calendars were tied to astronomy, particularly the cycles of Venus. The Maya tracked Venus's synodic period of 584 days with extraordinary precision. It was so extraordinary, it was enough to create eclipse prediction tables. Their astronomical observatories, such as those at Copan and Uxmal, aligned with these celestial events. However, math wasn't just for the stars and the pyramids. The Maya used it in trade, architecture, taxation, and agriculture. Their marketplaces functioned with currency like cacao beans, obsidian blades, and woven textiles. Their irrigation and planting systems required calculating seasonal cycles, rainfall expectations, and field rotations. Markets needed pricing systems. Tribute records were recorded with clear numerical glyphs on monuments, murals, and codices. For example, murals at Bonampak show tribute lists using dots and bars to represent payments in cloth, food, or cacao. Mathematics was woven into the social and political fabric too. Rulers often claimed their authority through grand calendar-based inscriptions, situating themselves in cosmic cycles as divine actors. Now, on to the Dresden Codex. It's not just a book, it's a time capsule. It is the most complete, best preserved of the 4 surviving Maya codices, and it's nothing short of a miracle that it still exists. handmade from a model, which is a type of bark paper, and painted with vivid natural pigments. The Codex is folded accordion style into 39 double-sided pages. When you unfold it, it stretches over 3.5 meters long. That's incredible. Scholars believe it was created in the post-classic period, likely between the 11th and 13th century CE, though its contents almost certainly draw from mathematical and astronomical knowledge handed down from the classic period, which was 250 to 900 CE. The scribe who composed the Dresden Codex was not just a writer, but a mathematician, astronomer, and ritual specialist, perhaps even a priest. Its pages are filled with tables predicting eclipses, charts tracking the synodic cycle of Venus, calendar calculations, and ritual schedules. There are gods, serpents, and symbols of fire, maize, and rain, each connected to a monument in time and a mathematical value. What makes the Codex truly remarkable is that it weaves mathematical precision with spiritual cosmology. So how did this ancient Mesoamerican manuscript end up in Saxony, Germany? Well, the exact chain of custody is lost to time, but it likely came to Europe during the early 1700s, perhaps taken from the Yucatan Peninsula by a Spanish colonial official, a merchant, or a missionary. It eventually entered the collection of Johann Christian Gotz, a theologian and a librarian, who facilitated its acquisition by the Royal Library in Dresden in 1739. At the time, it was admired for its exotic artwork and the novelty of its unknown script, but its content still remained a mystery. So for over a year, the Codex sat largely misunderstood. European scholars in the 18th and early 19th centuries had no frame of reference for its complex glyphs and numeric tables. Some believed it was simply an astrological almanac. Others assumed it was a work of mythology or fiction. Its pages were studied more as art than as scientific or mathematical record, because it was very beautiful. But that began to change in the late 19th century thanks to the efforts of a German scholar named Ernst Förstemann, the librarian who had become the first person to unlock the mathematical system of the Codex. Förstemann discovered that the dots and bars weren't decorations, they were numbers. He realized that the Codex contained base 20 calculations, tables of Venus's position in the sky, and precise calendrical cycles stretching thousands of years. So here's a little bit about Ernst Förstemann. I bet you've never heard the name. And his story is actually pretty interesting. He was a German historian, a librarian, and a philologist. He became the chief librarian at the Royal Library in Dresden. In the late 1800s, he began closely examining the Dresden Code. Forstemann's great breakthrough came when he realized that the repetitive symbols weren't decorations or astrological symbols, but numbers, written in dots and bars, structured vertically. He recognized the base 20 system and saw how dates and astronomical intervals related to real celestial events. Most crucially, he identified the shell glyph as a true zero, not a decorative flourish, but a number. This was groundbreaking. It was the first time a European scholar had acknowledged the depth of Mayan numerical sophistication. In 1901, he published his seminal work called Commentary on the Maya Manuscript in the Royal Public Library of Dresden, which mapped out the structure of the long count calendar and many of the astronomical tables, especially those related to Venus. His analysis laid the groundwork for modern Mayan mathematics and scholarship. But the Codex's journey didn't end there. During World War II, the city of Dresden was heavily bombed in 1945 by Allied forces. The Royal Library and much of the historic city was devastated. The Dresden Codex, stored at the time in fireproof archives, survived the bombings, but it suffered water damage from the firefighting efforts. Some pigment was blurred, and a few sections were nearly lost. But, remarkably, the majority of the Codex remained intact. Today, it is one of the crown jewels of the Saxon State and University Library in Dresden. It has been fully digitized and made freely accessible online, offering scholars, teachers, students, and the public a chance to engage directly with one of the greatest surviving records of Maya scientific thought.
We'll be right back after a quick word from my advertisers.
Following Förstemann's work, interest in the Maya grew, but it wasn't until the mid-20th century that Mayan epigraphy took off. During this time, great strides in understanding Mayan mathematics were made. Tatiana Proskuryakov, a Russian-American Mayanist scholar and archaeologist, demonstrated that stelae were not just mythological, they were historical records. Yuri Norozov, a Russian linguist, showed that Mayan glyphs were phonetic, not ideographic, as long assumed. And then David Stewart, starting as a prodigious teenager, cracked dozens of glyphs, tying them to real names, dates, and dynasties. These breakthroughs connected Mayan math not just to astronomy, but to language, dynastic history, and ritual life. Today, both indigenous and academic scholars work together to decode and revive this beautiful and rich heritage. So why does Mayan mathematics matter today? Well, Mayan mathematics offers a parallel development to classical traditions, demonstrating that complex systems can arise independently. It challenges the Eurocentric timeline of mathematical progress. Their innovations in zero, place value, and base 20 logic reflect a profound understanding of time and space. Rediscovering this knowledge not only honors indigenous intellectual heritage, but it also reframes how we think about the history of math. By preserving and celebrating Mayan mathematics, we gain more than numbers. We gain insight into a worldview that saw math as sacred, cyclical, and woven into the structure of the universe. The Maya just didn't do mathematics. They lived it. It was carved into stone, painted into sacred books, echoed in temple alignments, and inscribed into the very rhythm of daily life. Their math was not abstract and detached. It was sensory, celestial, and sacred. To study Mayan mathematics is to step into a civilization where numbers had personalities, calendars had souls, and time itself was a living, breathing force. In recognizing the legacy of Mayan mathematical genius, we're not merely filling a gap in the historical record. We're expanding the map of human imagination. We are reminded that there are so many ways to understand the universe, and the Maya, through their shells, dots, bars, and stars, offered us one of the most beautiful examples of how math resides within us and around us. Thank you for tuning in to Math Science History, and until next time, carpe diem.
Thank you for tuning in to Math Science History. If you enjoyed today's episode, please leave a quick rating and review. They really help the podcast. You can find our transcripts at mathsciencehistory.com. And while you're there, remember to click on that coffee button because every dollar you donate supports a portion of our production costs and keeps our educational website free. Again, thank you for tuning in. And until next time, carpe diem.